The simplest model to describe the behavior of electrons in materials is the free electron picture, where you have the atoms surrounded by the electron clouds, so the nuclei is surrounded by electron clouds, and the outermost electrons are free to move, free to propagate through these crystals, so they don't feel the attractive potential of the nuclei or the repulsive interactions between the electrons. Basically the most simple consideration you can have. So in the general case, the Hamiltonian consists of two parts. So you have a kinetic energy minus h bar square nabla square over 2m, and the potential energy, which depends on the coordinates, and this term is 0 in the free particle model. Sometimes it is called a Sommerfeld model or Drew the Sommerfeld model. The electron's motion along each coordinate axis is independent of the motion in the other coordinates, which is generally true in the absence of magnetic fields, where the cyclotron motion would complicate this behavior. But generally, this is valid approach, and you can write down the wave function which describes the behavior of electron in the material as the product of the wave function of individual coordinates. So psi of x, which is a function of x, times psi of y, the function of y, psi of z, the function of z. And the eigenvalues, so the eigenenergies then would be the sum of the contributions from each of those components. This then leads to 3 independent differential equations for each of the spatial coordinates. So in the x direction you will have h bar square over 2m nabla square, or you can actually write down because it's single coordinate, so d square psi of x dx squared equals e of x psi of x, and there will be something for x and y, for y and z, so just replace the x with y and replace y with z here, and then you can slightly rewrite this equation. So you rearrange the coefficients so you don't have any constants in front of second derivative. You get d square psi of x dx squared, plus you absorb all the constants into 1, it's kx squared psi x equals 0. And then you can express this constant in terms of what's left, so 2m ex or h bar squared, or you can express the eigenenergy in terms of this constant over 2m. So the solution to this equation would be, basically this is a second order differential equation, and you can have solutions written in different representation. One of the common ones is to use the exponents, and because it's a second order, so you will have 2 partial solutions where the general solution would be then the combination of those 2 partial solutions. If we only consider the direction along the x coordinate, you can have the wave propagating, for example, to the right. We'll have this psi x of x is a e to the ikx, and the another wave is propagating to the left, so the solution is psi of x equals b e to the minus ikx. The general solution is then the sum of the 2, so you will have a e to the ikx plus b e to the minus ikx, and analogously you will have a solution in the y direction, and the solution for z coordinates.